Hello, my name is Hassan Dabaja. I'm from the Laboratoire d'Informatique et des Systèmes at Aix-Marseille University. I'm going to present to you my paper, Overview of Sensors and Signals in Structural Health Monitoring, a case study on crack detection in a ship's hull. This paper is presented at the 9th International Conference on Control, Automation and Diagnosis, ICAD 25, which happens in Barcelona. The plan of the presentation is as follows: Introduction, Sensing, Time-based Signal Processing, Frequency-based Signal Processing, Case Study, and Conclusion. We will start with the introduction. Structural health monitoring aims to timely detect structural issues such as cracks. It is applied in marine, aerospace, automotive, mechanical, and civil engineering. Structural health monitoring systems encompass a network of sensors, data acquisition devices, and databases. The network of sensors is set in optimal positions to collect different types of important information. Data obtained by these sensors are analyzed with signal processing techniques, often coupled with machine learning algorithms. Signal processing aims to extract important features from the signals that provide insights into structural health. Traditional monitoring methods are expensive, prone to errors, and require human intervention. The development of sensing technologies has led to the use of advanced distributed sensor networks for automated monitoring. Sensors include strain gauge sensors, accelerometers for vibration monitoring, and temperature sensors. These sensors track structural responses to external loads, environmental conditions, and operational factors. Real-time data analytics relying on signal processing and machine learning allows optimal predictive maintenance strategies. The efficiency of sensing and processing has improved with the development of wireless sensor networks and IoT platforms. Crack detection is vital in marine engineering to ensure the safety and durability of ship structures. The hull must remain watertight to protect cargo, machinery, and accommodation areas. Undetected cracks caused by heavy loads, rough seas, or corrosion can escalate into structural failures, posing severe safety, environmental, and economic risks. Advanced structural health monitoring techniques enable early detection of defects, preventing catastrophic accidents, extending vessel lifespan, reducing maintenance costs, and enhancing overall safety for cargo and crew. Strain sensors are suitable for monitoring cracks by deploying it over fatigue-prone areas to detect abrupt strain changes due to cracking. Examples of sensors used are accelerometers, strain sensors, ultrasonic sensors, acoustic emission sensors, linear voltage differential transducers, fiber optic sensors, load cells, corrosion sensors, and visual inspection devices. Sensors are connected to form a network to give a holistic view of structural health. Information collected include acceleration, strain, velocity, and displacement. The aim is to detect and locate damage, such as cracks. Structural health monitoring techniques are categorized into local, limited to the sensor's area, and global, capable of detecting damage through the structure via sensor networks. Types of recorded parameters include load parameters. They delve into the forces acting upon the structure, encompassing static and dynamic forces such as wind, speed, and loads. Global load response. It delineates the structure's reaction to a given load, measurable across the entire structure, typically encompassing parameters like acceleration and velocity. Local load response. It focuses on a specific part of the structure, measuring parameters such as strain, cracks, and tension forces in response to a given load. Environmental factors. They are external to the structure and encompass parameters like temperature, salinity, humidity, and atmospheric acidity, aiding in estimating environmental loads like wind. Sensing data must be collected over a sufficient period at an appropriate sampling rate. The strategic positioning of sensors at various locations is important to capture the structural response. To optimize the placement of sensors in a network, engineering requirements and design considerations must be both balanced. Sensors placement problem is complex, requiring heuristics and optimization algorithms. Algorithms aiming to solve this problem include effective independence method, hybrid Firefly, and genetic algorithms. An important sensor in a structural health monitoring system is the accelerometer. It provides real-time data detecting vibration and movement, aiding in the identification of cracks, shifts, and other stress-related damages. There are a lot of examples regarding sensing and structural health monitoring. Rami et al. Used triaxial accelerometers for crack detection in concrete structures. Joseph et al. Used piezoelectric wafer active sensors to precisely estimate fatigue crack. Mioni et al. Used a new piezoresistive sensing technology to monitor strain and detecting cracks in masonry structures. Tan et al. Used distributed fiber optic sensors for accurate crack detection and quantification in engineering structures. Time-based signal processing techniques. Signals collected are used to create mathematical models and extract structural dynamics. Time series analysis is extensively used for extracting features from time domain data, where parameters or residuals of autoregressive models serve as frequent indicators of structural damage. Statistical time series models can be either linear or nonlinear. Linear models can be stationary or non-stationary. Stationary models include autoregressive moving average and autoregressive moving average. Non-stationary models include vector autoregressive, autoregressive with exogenous input, autoregressive integrated moving average, and autoregressive average with exogenous input. Some examples. Chejeni et al. Developed a method for structural damage detection using Kullback similarity and improved autoregressive modeling, focusing on identifying damage location and severity through vibration data analysis. Rajiv et al. Introduced a novel approach for detecting damage in reinforced beam column joints using adaptive autoregressive modeling. Anastasia et al. Developed an approach using autoregressive modeling to continuously extract damage-sensitive features from strain data collected on a railway bridges. Guo et al. Utilized vector autoregressive modeling and Bayesian inference to detect structural damage in bridges from ambient vibration data. Lakshmi et al. Introduced a decentralized damage diagnostic technique for high-rise buildings, utilizing the vector autoregressive with exogenous input model. Yu et al. Proposed a substructural approach for damage identification in complex structures, introducing a substructural autoregressive moving average with exogenous input model. Discuss frequency-based signal processing techniques. Frequency plays a significant role in structural dynamics. Structural characteristics such as stiffness and damping are frequency dependent. Damage in a structure such as cracks can alter its dynamic behavior. This includes changes to natural frequency, mode shapes, stiffness, and damping ratios. To detect and analyze these changes, various frequency-based signal processing methods are employed. Commonly used techniques include spectral analysis, discrete Fourier transform, frequency response function, strain frequency response function, frequency domain decomposition, and multiple signal classification. These methods enable the identification of structural damage and the assessment of dynamic responses in monitored structures. See some examples. A method based on cyclic spectral analysis and spectral correlation was introduced by Prawin et al. For detecting, localizing, and characterizing fatigue breathing cracks in engineering structures. A wavelet-based damage index was developed by Zhu et al. To locate and estimate the crack depth precisely in functionally graded material beams. Pu et al. Introduced an optimized-based damage quantification using FRF to explore the usage of damage detection approach in an experimental reinforced concrete beam model. Perez Ramirez et al. Produced a music-based technique for detecting and localizing damages in a truss structure under various dynamic excitations. Now we will discuss the case study of the paper. Long-based strain gauges are used to measure strain over an extended length of an object's surface, offering a detailed understanding of strain distribution. A sensing network of 18 sensors is placed in different locations of a ship's structure. The data collected by the 18 sensors are of 5 months of continuous monitoring. The goal is to analyze the data to get an insight into the health of the ship's hull structure. The aim is to track the strain during the period of study to detect the existence of a crack. The proposed method is as follows. Divide the strain signal epsilon of t into equally timed signals epsilon I of t. For each of the formed signals epsilon I of t, compute the power spectral density. Deduce the peak values, peak epsilon of I. Continuously monitor the peak values. If the peak values are greater than a threshold E max, then a crack exists. The strain signal is divided for each sensor in the data to 3,685 shorter signals, each having a duration of 1 hour. The peak value of the power spectral density is found at frequency of 0 Hz. The peak recomputed for each 1 hour signal value for the whole 6 months of recording. Results show no significant increase in the peak values for all the sensors. This implies that there is no obvious occurrence of cracks during the period of study. However, to evaluate the algorithm, it is needed to have data with and without cracks, and to compare the outcomes in each case. Conclusion. Effective sensing and proper sensor placement are essential for the quality of the collected data to detect defects. Sensor technologies include strain gauges, accelerometers, and fiber optic sensors. Signal processing plays a fundamental role in extracting meaningful features from sensor data. Signal processing include time domain and frequency domain methods. A case study of fatigue crack detection in ship's hull was presented. Long-base strain gauges sensors were used to monitor structural integrity over an extended period, and a methodology based on power spectral density analysis was applied to detect potential cracks. The results demonstrated indicates the absence of detectable cracks. Further validation is required by analyzing datasets containing both cracked and non-cracked conditions. Further work may incorporate advanced machine learning techniques to enhance detection accuracy and improve early fault prediction in marine structures. And thank you very much for your attention.